Good morning, everyone. Welcome to the second day of RAAD. We hope that you enjoyed yesterday, and we also promise you that today will not be worse. So we'll do our best, and we also have great speakers to contribute to my statement. So, and we'll start this day with a great talk about a hot topic in robotics, about humanoid robotics, to discover is it hype or the next big thing in AI. And I'm honored to give the floor to Alin Albu-Schäffer from DLR, Institute of Robotics and Mechatronics and the Technical University of Munich. I will say a few words about Alin, but I believe that you know a lot of already. So Alin received his master's degree in electrical engineering from Technical University of Timișoara, Romania, which is less than 200 kilometers far away from here. And his PhD in automatic control from the Technical University of Munich in 2002. And since 2012, he is head of the Institute of Robotics and Mechatronics at German Aerospace Center, DLR. Moreover, he is a professor at Technical University of Munich, holding the chair for sensor-based robotic system and intelligence assistance systems at the School of Computation, Information and Technology. His personal research interests include robot design, modeling and control, nonlinear control, flexible joint and variable compliance robots, impedance and force control, physical and human-robot interaction, bio-inspired robot design and control. He received several awards, including IEEE King San Fu Best Paper Award and the Transactional Robotics in 2012 and 2014, respectively, several ICRA and IROS Best Paper Awards, as well as a DLR Science Award. He was strongly involved in the development of the DLR lightweight robot and its commercialization through technology transfer to KUKA, and he is the coordinator of EUROBIN, the European Network of Excellence in Intelligent Robotics, IEEE Fellow and RAAD member. So, Alin, thank you once again for joining us, and the floor is yours.
Hello, good morning, and welcome everybody. It's a really great pleasure to be here. I haven't been in Belgrade since, I think, more than 30 years, although it's close to my hometown, so I'm very happy to be here and see also some very good friends. We had Costa spending some time at DLR more than 10 years ago. And this is a great conference and opportunity for interaction. So, I decided to talk about humanoids because, just a second, this was not the title, because this is such a hot topic, and all, the newspapers and journalists, they want to hear if the robots are coming today or tomorrow, and if we will all remain without jobs, or how life is going to change. And I think we need to give a good answer to also, not only to media, but also to the society, because they are worried, but they also get some expectations which might be unrealistic. So I will try to give our perspective, and what triggered the whole discussion is events of the CEO of NVIDIA, for example, this year in Las Vegas, where they presented all or a lot of humanoids robotics, prototypes from the US, and then the CEO said AI has been advancing at incredible pace. It started with perception in the AI, understanding images, words, sounds, then generative AI, which was kind of a surprise for the whole society, creating text, images, sound. But now we are entering the era of physical AI, AI that can proceed, reason, and act. And we all know it's much more difficult to act in the real world than acting on text from the internet. And there are, I have several of those citations, and probably the most important was Elon Musk's comment like 2022, where he said in principle that, with humanoid robotics, Tesla will make more money than with cars and with autonomous driving, right? I mean, now you could ask, is it a way of sustaining stack exchange value, which is overrated of a company, or does he really believe, right? But he did big changes, right? Or ChatGPT moment is coming. Some people talk about iPhone moment. So what they are talking about is that robotics is going to be ubiquitous, And as the smartphones became, a commodity for everyone in the early 2000s, this kind of robots would come in a similar way, right? And we can imagine that this will be a bigger disruption than smartphones and a bigger disruption than ChatGPT if you will see the numbers they are talking gets true. This is a statistics again from, these are 2 or 3 slides I have borrowed from Michael Wang's plenary on humanoids because he has such a beautiful plenary about humanoids in China. But I don't know if you see it well, maybe I stay in the way, maybe I go to the side a little bit, but you see the forecast, of course, is overly optimistic, right? They say we start with manufacturing, then go to business and family in the 30s. So it's like every one of us at home will have a humanoid robot in the 30s. We all know it's very optimistic. It's not true. To be honest, right? And then they are talking about this kind of numbers. If I read them correctly, they are talking about selling 10 billions of humanoid robots by 2030. I mean, it's a crazy number, right? But if journalists read that, they say, should I believe or not, right? Is it true or not? And they come and ask us, right? And of course, they are exaggerated, but on the other side, there's so much money in the system, right? I mean, after Elon Musk said something like that, he did, reusable launches, all these satellites, he did PayPal, he did Tesla, I mean, establishing a market for electric and autonomous driving. And very often the Chinese just followed and did it cheaper, right? And that's what the Chinese said this time. Okay, Elon Musk is going to do a mass market on humanoid robotics. We are going to follow and do it cheaper. And they have in China 4 areas where they announced to invest 140 billion euro just in humanoid robotics in the next 10 years. I don't know if those numbers are true or exaggerated, but when you speak to Chinese colleagues, they say, if you know how to spell out humanoids and have a company, you can go to government and take millions of dollars for investing in humanoid robotics. And this led to more than 100 companies doing humanoid robots just in China. I think they are probably this number is still already old, but at the time, beginning of the year, there were like 120 companies, 130 companies doing humanoid robots with no market yet, right? Have you seen any humanoid robot in a factory? I haven't, right? But you have 130 companies with a lot of investment, and you have seen the YouTube videos, which are impressive. So what are we doing in Europe about that, right? So robotics used to be, if you look at KUKA, ABB, FANUC, they sold maybe 30,000, 40,000 robots per year, right? Which is still moderate for scaling, right? If you talk about 10 billion robots, even about 1 million robots per year, so you have completely different production methodologies. We all know about smartphones, right, how integrated they are because they sell hundreds of millions per year, right? So can we imagine a robotics industry, exploding like this and going into the billions? This is what they are talking about, right? And what are we doing in Europe, right? We don't have the private money of Elon Musk or American investors. We don't have the governmental support from China. We have small things, but still some things, right? So Costa mentioned, I'm a coordinator of a network of robotics of which some of you are partners, the colleagues from Ljubljana, IIT is part of it, several colleagues, right? So we try to put together 31 partners from some of the best labs, and then we have cascade funding, and I'm very happy that in the cascade funding we have all also Eastern European countries. Basically we covered, so these are the core partners. Meanwhile, we covered all the countries from Europe, about 70 partners, and we are trying to unite forces of research in Europe to give an answer to that. And we are addressing 3 main application areas: robotic manufacturing for circular economy, then personal robots, so the humanoids more or less, and then outdoor robotics. But the idea is that we design the research in such a way to enforce exchange between partners. So we have what we call the Eurocore. It's if you Google for Eurocore, it's a cloud infrastructure where all the participants are invited to upload their code and their data to train jointly models. And then we organize what we called co-petitions, so cooperative competitions, where the teams are valued more points if they solve a problem with the algorithm of a peer than with their own algorithm. For example, IIT won the outdoor robotics challenge because they had a lot of cooperation with many partners, of course, with PISA, with Antonio Bicchi's lab, but with many other partners as well. So I would say they were very good. Maybe they were not better than others in terms of, they were similar in terms of performance. They were very well linked and interacted. So, and they won this competition for that, right? And our idea is, you know, the question for the network was how to best learn and benefit from each other. And we said from a network of humans to a network of robots. So we have plenty of cool robots in Europe, but no lab is big enough to solve all the problems alone, right? So the mantra of this project is transferability, and we have also a lot of cascade funding projects. And with this transferability, we hope to, you know, to bring everyone further. Every year we have some networks with interactions, plenaries like this one, but also what I mentioned before, the cooperative competition where we had about almost 200 people, you know, competing according to those rules. Last time it was in Annecy, and I can show you just some of the images. So the personal robot challenge, this is our robot Justin, was the following. We had 3 different kitchens brought by Karlsruhe, DLR, and INRIA in France. And 40 objects, the YCB database. And the judges came and say, you know, pick that object from the dishwasher and bring it to kitchen 2 and give it to human. So these were the challenges. And if people could not perform, they had a kind of a joker to simplify. You see driving systems from ATH. This is Sevilla with a flying drone and manipulation. I think you have seen before this is the Centaur from IIT, from Nikos Zagarakis. You know, very different morphologies. This is the Tiago robot from Portugal and INRIA in France. And you see, still using sometimes markers for the vision. This is Alter Ego from Antonio Bicchi in Pisa, and so on. So it's impressive, but we still saw that the robots are capable of doing a lot of things, but they are still slow, and they are doing still a lot of errors and mistakes. So we reached some things, but the way, I think, is still very long. Okay, now after this introduction, I will try to address some aspects about where I think we are from our perspective, from DLR, starting with hardware and control, then autonomy and AI, and then a little bit of applications. Okay, so robot design, actually, you know, maybe the first robot which was really impressive came from Japan, and they started at Honda maybe in the 90s already, and this was the Ashimo robot, and if you look at most of the robots today, they did not change too much. So Ashimo was a rigid position-controlled robot with force torque sensor at the feet. What we pushed forward was the torque-controlled robots. I will talk more about that. But there are also different designs. I know that Costa is looking into elastic robots. I'm looking also into elastic robots. Now there's a big change coming from China in quasi-direct drive robots. They are much more cheap because they have very cheap gearboxes, they don't have torque sensors, and they have impressive speed and torque. So there has been massive progress in actuation in the last years, obviously. But most of them are in the first 2 categories. And talking about zero moment point, no, first of all, I want to talk about something else. Why do I think that it won't be 3 to 5 years, but at least 10 to 15? You know, I have this experience, Konstas mentioned that, of developing what we called cobots, lightweight robots. And I started as a PhD student after finishing my master degree close to here in Timișoara. I started here in '95 as a PhD student, and then we did about 8 years of research. So this is somewhere here I did my PhD. And then we had a robot where we thought, oh, it's a good prototype. We can, you know, license and commercialize it. And we licensed it to KUKA. It was around 2006. And then it took them about 5 years to do a serious product. until 2009, and then several robots came out of that. Franca Emica, I'm very happy to see Sven Parusel here, who has been, I don't know, about 8 years with DLR, or something like that, right? And here now is the coordinator of research collaborations at Franca, Agile Robot, who bought Franca, and many others. So, you know, this was a journey of maybe altogether 20 years until you get those in the market. Of course, the market was evolving slower. You did not have an Elon Musk putting money into that. But still, getting a nice prototype in the lab into a serious product takes you 5 to sometimes 10 years in robotics. That's the hard lesson we learned, right? When I graduated my PhD, I thought in 5 years everyone will buy those robots, right? It took. Now we license this to medicine. We started now a company to do this in space robotics, and we use those joints from the KUKA robot actually to build our humanoids. Because, you know, I learned that as soon as you have a good module for actuation, it's pretty easy to build more complex robots. If you did your homework on actuation, communication, low-level control, and so on, getting a humanoid out of the arm was a matter of 1.5 years. Okay, now, since we are here in Belgrade, I have to give a reverence to one of the two main contributions maybe from the University of Belgrade, which is Vuko Bratovic's work. 1968, it's 57 years. I know it so well because it was the year I was born. So, and still, you know, they defined this concept of zero moment point. Still, Ashimo in 2006 and 12 still worked with zero moment point, and I think still some of those robots work with that. We don't. We have some other approaches, but this was one of the most long-lasting contributions in robotics, maybe. So what do we do instead is using joint control and doing basically a coordinated control of the whole body. And actually, it was Christian Ott and some colleagues on Humanoid 211 from DLR, where they realized actually manipulation with the hand, moving object with the hand, and balancing on legs, they are similar problems, basically. You have parallel robots, parallel actuation, and you have an object which you would like to manipulate, and you have unilateral constraints with a friction cone. Whether you manipulate the object or work and the object is the ground, right, the mechanics behind is in principle very similar, right? You would like to have some controller in this object frame or in the body frame, and then distributes the control forces on the joints under consideration of the friction constraint. For example, for our robot, if the robot is just balancing, you have an impedance controller keeping your center of mass in a certain place with a spring and damper controller. That's the simplest thing, or you can start giving a trajectory to the center of mass. Then you define this spring and damper in those coordinates, and then you have a potential, and by differentiating this potential with respect to all the joints, you generate a rotation and a translation controller. Then either somehow you need to get its force distributed to the joints by pushing to the ground, right? And on the ground you can only push, you cannot pull, so you have some friction constraints which you need to take into consideration. So by just constructing the Jacobian matrix and then having the additional constraints that the forces need to be minimized and to stay within the friction cone, you can solve this numerically. Actually, with current numerical algorithms, you can solve it within 100 microseconds, maybe or so. And these are some results where the robot is just keeping the center of mass. It can keep also different other coordinates, like the TCPs of the arm. You can move the entire body, and you can solve, for this multilateral contact with a parallel structure. You can handle singularities, redundancy, all this range distribution by just using the torque interface and this optimization control framework. Let's see. Oh, for some reason, could you click on the videos, please? For some reason, okay, it just took a while, sorry. So what you see is because you have a very fast control rate, the robot is even adapting for unknown terrain. So basically, the robot is not knowing that it's balancing on this rocker. It's just trying to keep the center of mass in the given position. And then this force distribution optimization just optimizes every 100 microseconds, basically, for this balancing. Okay, let's move on. The same way, the good thing about this torque interface is that you can handle unknown environments. So like pushing this object, you just define a frame for the center of mass, frame for the arms and the legs, and then you can interact with the environment because we have this passivity-based framework which controls the energy of interaction. I don't have the time to go in details, but if you know my research of passivity-based control, this is the framework we are using. Now, of course, what I have shown you so far is just controlling the center of mass, right? But when you start walking, right, you need to define trajectories for this center of mass. And the difficult thing about locomotion, biped locomotion, is that bipeds are unstable. So walking is kind of a continuous falling forward, right? So in terms of differential equations, this manifests in the fact that if you write down the equation of motion, you don't need to look at the details for the center of mass. But the point is that you have two first-order differential equations. One is stable and one is unstable. And basically, I'm sorry, what's going on? Just a second. Yeah, probably I have. Okay. Yeah, maybe one slide is missing. But the main point is that you have two differential equations, a stable one and an unstable one, and the way of computing the desired trajectory is to integrate forward from some step planning to integrate forward the trajectory for the stable part, and to integrate backwards in time the trajectory for unstable part. And this way, given some trajectories for the foot planning, you can generate with analytic solutions trajectories for the center of mass. And these additional points, actually the planning framework which we developed is, instead of working with differential equations like this, you define some auxiliary points. And maybe the most important point is this divergent component of motion. So this is the center of mass. This is the divergent component of motion. You can understand basically walking by imagining, and then you have a third point, which is the virtual repelling point. So you can imagine walking like you have a point which you need to plan. Then this red point is repelled unstably from this virtual repelling point. So this is the unstable part. And the center of mass follows in a stable part. So this is diverging and this is attracting. If you integrate in time backwards, basically this is also converging to V. So basically you can integrate this differential equation in one direction, the other differential equation in the other direction, and get the entire step planning. Okay, and these are the results of this trajectory step planning. What we plan is actually just the footstep trajectories, and automatically out of that we generate the center of motion trajectories. And again, because of this balancing property and this force distribution property, you can walk on uneven terrain, you can walk on rocks, and the robot compensates for that. So you don't need to know exactly on what kind of terrain you are actually. And okay. Now, people expect us to do learning, right? If you go to the conferences, if you are doing model-based control today, everyone says, oh, you are old style, right? You need to do learning. So I told my PhD students, you need to do learning. And but our convention, at least, I'm coming from a model-based world, is that it makes sense to do learning on top of that, instead of learning everything, the entire balancing and so on, because there are a lot of free parameters which you can adjust. For example, adjusting angular momentum such that you can increase speed, right? So we take this framework, and you still have a lot of space where you can plan these trajectories for the center of mass, for the virtual repelling point, and so on. And this is what we are learning, basically. And by learning, you can, of course, substantially increase the performance. But again, I'm pretty convinced that you can reduce the space in which you optimize by just taking a model-based approach. And of course, you can increase working speed. So I have to say that we cannot run, as you have seen in the Chinese videos, a half marathon. But this is mainly a limitation of the speed of those lightweight robots joints. So they can just turn 180 degrees per second. So now we are preparing a new technology where you can increase the speed. But in principle, the control approach goes at the limits of what the hardware can currently do. Now, of course, how do we handle, walking forward on a straight plane surface is one thing. How do we handle disturbances, right? And doing humanoid robotics is also looking at humans and understanding how do humans react to perturbations, for example. And humans have different ways of reacting, right? The first reaction for small perturbations, you try to do it from the ankle. Then the next is a hip strategy, where you try to balance from the hip. Then the first one is, you go down to the knees if you have too much vibrations, and then you do a step backwards. And this everything can be put into a pretty nice framework, actually, with the formulation with the virtual repelling point I mentioned. And you can very precisely say, what are the limits of stability. So this is, the center of mass. And again, this is a paper we just published in RAAD. But you can very precisely say, when you go in which strategy. So in the first phase, you try to, do ankle control. Then you go to the next phase with hip, and then you start doing with the arms and compensating for the angular momentum. But you see, there's still a very big space to explore. So you can use a lot of learning to become better in this area. But what you see here is still completely model-based, right? Compensating the angular momentum, the center of mass dynamics, and so on. And you can even go on one leg, and the robot can compensate it until it reaches the velocity limits, right? Again, we have a limitation on the speeds, but I think also model-based control can be very powerful and reacting, and again, putting machine learning on top make things even better. These are just some more examples. And all this natural motion actually emerges from simple first principles, like stabilization of the center of mass, conservation of angular momentum, minimization of interaction forces, and keeping the friction cone constraint satisfied. Okay, now, this is the robot working. This is Robert Schuller, one of my PhD students. One thing is you can really interact with the robot. This is a lightweight robot with torque control. If you see at the Boston Dynamics former Atlas robot, they had to push from the distance. We also pushed at the beginning from the distance. But actually, it's a robot which is compliant, like the cobots are, and you can directly interact with them, right? Okay, now this can be extended also to running on uneven terrain. Unfortunately, we cannot run with our robot, as I said, because we have some velocity limitations. But the framework, this is a pretty precise simulation. And using this concept of center of mass, divergent component of motion, virtual repelling point, you can also program things like running and just a second. Video is very slow, I'm afraid. Could you maybe help me by clicking on the video? Oh yeah, thank you. So you see the only thing you need to plan are the footsteps. And then this algorithm automatically integrates, generates the trajectories of the points I mentioned. And then you can generate a transition from walking to running, and then back to walking. And then even you can, maybe I'll jump over that. You can even, vary the trajectories, run in circles. And this is always solved online in a millisecond planning level. We are building now a robot and hope that we can demonstrate this in real. We also bought one of the Chinese robots, which do not have these limitations, but they don't have torque interfaces. So all these model-based approaches do not apply so well, I have to say, on the quasi-direct drive robots, because they have a lot of friction in the joints. So there's a serious limitation. The methods we have apply for torque interfaces very well. Okay, now maybe I'll jump over that for sake of time, and just discuss about, again, learning and reinforcement learning. Because I've shown you, there's a lot of parameters which you can place, for example, the places where you place your foot, the way the leg swings, the swinging of the arm, the placement of the center of mass in this environment. Everything can be learned either by black box optimization or by reinforcement learning, and this is what we are looking at, but on top of the model-based control. And this is some really very late result of a master thesis, and this is really the maximum joint velocity this robot can do. So, you go from 75 centimeters per second to 44 centimeters per second, which is the maximum our robot can do by using reinforcement learning on top of the model-based approaches. Okay, I'll stop here on that point and just to summarize this control framework. Everything is based on controlling the interaction forces for the tip of the arms, for the legs. And then you have object compliance control for the hands. You have the center of mass compliance. You have a null space compliance, feed-forward terms, everything integrated into one framework. And then you can do manipulation and locomotion with the same system. And maybe I'll jump over that and come to the next point, which is about AI and autonomy. And saying that I talked to you a lot about legs so far, about humanoids. And actually, our people working on hands love to show this homunculus. This just replicates scales the human body respective to the sizes of the different cortex areas in the brain. So in our brain, in the motor cortex and in the sensor cortex, the area for the hands is much, much bigger than the area for the legs, actually. For the hands and for the mouth, for the lips, for talking and so on. So obviously, looking at this, it looks like manipulation is much more complicated than locomotion. And people, which are happy to show some humanoids running, they don't realize that if you want to go to the market and solve that, you need to solve the hands and you need to solve advanced manipulation. And this is the second credit I would like to give to Belgrade University. This, of course, I think Nicola showed me yesterday in the museum upstairs the first robotic hand, which also came from Belgrade. I found the paper also 1968. I think it's even older, but this is a quite often cited paper. So very impressive, right? And this is the next big thing we need to solve. Now, just at the beginning, very classical approach, right? You need to plan your center of mass motion in order to, first you localize objects on the table, then you do some grasp planning and iterate over all possible grasps. You do the localization and then do the planning of the entire motion to grasp the object. This was a very classical approach, but this shows the complexity, right, of grasping and manipulation. First of all, we localized the objects and approximated them by spheres and cylinders and cubes to easily generate grasps, right? Then you localize their center of mass, and then you generate a lot of random possible grasps, you eliminate occlusions, and then basically out of the many possible grasps you can generate, you pick up some of them which can be executed. Now we have this perception pipeline for this database. Maybe if you work on vision, you know that. This is this YCB object database. This is Whale, Carnegie Mellon, and Berkeley. So basically there are about 40, 50 objects from Walmart, right, in US, and you know, they are considered a standard benchmark. So we can identify and localize those objects on a flat table, right? And then after localizing the objects, the algorithm is generating like 100 graphs. Basically, those graphs had been generated beforehand because you have these object primitives, but you adapt those graphs to the localized object, and then basically you do a graph feasibility check and select out of those 100 graphs the graphs which can be best reached by the arm of the robot, right? And then, of course, you need to analyze the workspace, so to have some motion planning for the robot, to avoid singularities, we have this capability map, which tells you, where the robot can reach the objects. So grasping and manipulation is a very complex pipeline, right? And at the end, you need to generate the locomotion to get there. Well, and this is the outcome. This is a demonstration in a project we had with Airbus maybe 4 or 5 years ago. Right, we have these objects, you localize them on a table, the robot needs to move there, generates the grasp, and grasp the object. It's very simple, right? If you show it to journalists say, oh, my 5-year-old kid can do that much faster than your robot. Yes, that's true. Yes, that's true, and we need to go faster, but after you explain what are the humans solving, what are all the tasks we are solving in a sequence, maybe people get some respect on the performance of humans and on the performance of roboticists, right? That we have really a hard job to solve. Now, of course, this is very model-based. Now machine learning came and everybody said, oh, I don't need to learn homogeneous transformations anymore. I just feed it into my learning system, right? And they are good. So this is, for example, in-hand manipulation, right? And this is something fully trained on this side from data. This is model-based. I still, push my PhD students to do both, right? You will see it can turn the cube for minutes without falling, and only based on position sensing and internal force torque sensing. And the way those motions were generated were purely in simulation. So you have a simulation with pretty good friction models, right? And then it optimizes for 45K steps, 3 million steps. So you do a lot of simulations, parallel simulations with thousands of hands and thousands of cubes of different sizes and different friction. And then after that, you are able to turn the cube. I have a PhD student who did it also model-based with Kalman filtering and more classical. It works as well, right? And yeah, I tend to hope that, again, having the model-based approach and putting machine learning on top is more promising in the long run, but I'm getting more and more isolated with this opinion in the community. And some people just think you just need data and nothing else, right? And then use TensorFlow from Google and then everything will be solved. Let's see. The future will show it. But even solving these kind of things is challenging, right? They train for a week for just manipulating cubes. Now they are able to manipulate different objects as well. Motion planning, of course, you can do motion planning the classical way, but you can do motion planning by learning. It's a very high-dimensional space, so I still think that there's a lot of model-based solutions to be given here. But what data people do is they generate random environments, right, with random obstacles, and then massively train with GPUs. Don't care if you need to train on, I don't know, you need an atomic power plant to get the energy to train that. You do it massively, parallel in simulation, and then you get some good solutions. So that's the big promise, that in the future, we don't need all these tedious mathematics, but you just need data and big computing power, and then you will solve robotics. And if you attended ICRA, there's a really strong debate on that, right? What's the future of robotics? Another thing I was, there's a group, this is Bertolt Bäumel's group. This is again a machine learning approach on grasping objects. You look with the camera, you just see one side of the object. Then you can complete the shape. How can you complete the shape of what you haven't seen? Of course, if you have seen millions of objects in simulation, you can imagine that how it looks on the other side. After completing the shape, you can generate a grasp, and this happens in 1 second. And then the robot goes there and grasps the object. And it works really robustly. If you have one object on a flat plane, you can go there and put your shoe and the robot will grasp it, right? And those things work meanwhile pretty robustly from simulation. So image, shape completion, grasp generation, grasp execution. How do we train that? Because we have great virtual worlds. We have also an open source simulator where you can just generate random words, drop objects on that, millions of objects, and then in these words you have automatically the segmentation because you generated those objects. And then the people train vision on those virtual data. And those virtual data are getting more and more precise. So now the quality of the object localization is getting better and better. So that's a pipeline we are using for object detection. First, you need to localize the object, right? To detect the object. So just to say, I see 2 cups and 1 plate. Okay. But that's not enough, of course, right? In addition to detecting the objects, you need to localize the 60 pose, which is different from what people are doing on the internet, right? They just want to see if, what kind of t-shirt are you wearing, if it's Nike or Adidas or if it's a cat or a dog, but we want to know at precision of millimeters where the objects are. So that's the next aspect of the pose estimation. And then we do some local refinement by tracking the objects. And here you see some video of the robot, unloading the dishwasher. Still pretty slow, but first of all, we open the object on a feed-forward trajectory. But that's what's very important to us is also the fact that we don't only localize the object, but we also localize the hand, and we do relative transformation, so visual surveying. You will see right now, so the robot is first identifying and recognizing the own hand. This is over here with the overlay. And then the robot is going and then identifying, the plate over here. And then it can do a relative motion, a tracking between the hand and the object instead of having absolute motion for, an absolute motion for an absolute pose in space. You are controlling the relative motion between hand and object. Okay. I think I stop here and come, well, what are we doing with large language models? Everyone is asking, what are you doing with LLMs? We are using them mainly for explanation, right? And I will give you just a very small example, right? And what we think is that foundation models, maybe explain on this, right? Our brain is not an end-to-end big network, but you have a perception cortex, a motor cortex, world model, an action part, and so on. You have the brain stem where you have the local control and so on. And I still think that also in the future, I don't believe the end-to-end approach is the one, but I think we will have, neural networks and foundation models for parts of this architecture, right? And where we have been successful is using large language models to explain the state of the robot. Very often when you ask a language model, you download it for the internet, and you ask the language model, do you see a coffee machine or a microwave? Of course, the language model can see it, but you don't know if the robot has recognized it, right? But if you connect the language model with the internal architecture of the robot, right? So I would like the language model to say, I don't see the microwave hour because the robot doesn't see it. I can see it. So such that you get informed about the internal state of the robot, because laymen have problems understanding what's going wrong with the robot. You need to check for singularities, for object has not been detected, for being out of reach of the arm. And I would like the language model to provide explanation to people about the state of the robot. And we had an experiment with astronauts where the language model is doing exactly that. So, the astronaut is controlling a robot, and then the astronaut does not know anymore, what can the robot do? What kind of feature has the robot? And we use the language model to provide instructions to the human about how to use the robot, but also help them for troubleshooting. So for example, you can ask the robot, how should I teleoperate, Justin? And then the language model tells you, you need to use the input device, and then you press C for this and press B for that, and first you need to release the button and so on. So this is one of the points, right? Connecting the large language models with the internal state of the robot and with the documentation and with the state machine of the entire robot. I think this is a promising approach. I would like to use my last, may I use 5 more minutes? Yeah? For some examples of applications. I'm coming from the area of space, so we are doing space for orbital robots, space for planetary exploration, but also space for assistance, right? And to every space area, we have connected a terrestrial area, and I will give you some examples from space assistance, but also robotics for elderly care. Why space assistance? Bringing an astronaut in space costs billions, right? 1 hour of astronaut operation on the space station is $100,000. Right? So it's very, very expensive and dangerous. And we believe that robots can be a big help in space exploration. Elon Musk again announced in 2 years he will bring a humanoid to Mars. Let's see. Right? But we did a lot of experiments with astronauts to understand how they would like robots to assist them, right? Or even to prepare everything, right? So I made a bet with Alexander Gerst, and I told them, I'm pretty sure we will have a humanoid on Mars before a human, and when you arrive on Mars, the robot will give you a welcome drink. Okay, let's see if we will come to this point. But what we are doing is, the astronauts are on the space station, and they are assumed to prepare a station on Moon. So he's on the station on Mars, around Mars or Moon, and he's preparing everything for his landing. And you have the robot down there preparing, the solar panels, doing some maintenance, doing some repair. In some of the cases, some smoke came out, and then they have to replace one of the elements. And the astronauts can decide to use the humanoids either as a teleoperation, where they can go into the avatar and command the robot, or to use their AI features. And just some newest developments from the European Space Agency. The European Space Agency, they wanted to contribute to the American Artemis mission, but now Trump decided to stop the Artemis mission. So now Europe thinks about building own humanoids, and they developed this AI, just an AI visualization. And then we took our robot Toro, and within 2 days, we went to our base floor and could replicate at least some of the motions of the one from the AI-generated video, So the robot worked on a Moon environment, and then it took this cover and covered the robot with a blanket. So I think the area where I'm paid for, space exploration, robots, also humanoid robots, but also rovers, can do a lot of big help. But more than that, I think the robots can help on Earth, and this is what we are expecting today. We are dreaming of having robots everywhere, helping in our homes. I don't know when this will happen, but we have a big challenge, a big demographic challenge. I don't know the situation in your country, but in Germany, these are the people who will retire in the next 10, 15 years. And these are the people coming into the working area in the next 10, 15 years. In Germany, there's a delta of about up to 500,000 per year. We will be losing 500,000 people out of the 40 million which work in Germany every year. computed for Europe is the same, US is the same, even China is the same. We'll lose many, many million of people. You know, in the 80s, 90s, we had this plus, right? Now we have this minus. So especially in the area of healthcare, we have a big challenge because, you know, there will be more elderly people, less people to give care. So there's really a big challenge to address that. So our approach, of course, the robots cannot solve the problems alone, right? But what we imagine is having a robot to help people at home. You know, my mother still lives in Romania. I live in Munich. She lives alone. I would like to have such a robot where, you know, sometimes I can, you know, dive into the avatar and help her finding the glasses on the floor. So, you know, accessing the robot over a tablet interface like the astronauts did. But then when it's getting serious, you would like to have maybe caregivers which are trained from the hospital, from the call center, and they can be everywhere, not only in a hospital in your country, but maybe even from another country, you know, diving into the avatar and helping the people. So, you know, you use the AI when the AI works, and you rely to humans when the AI doesn't work, or if the humans want to interact. So, you know, this kind of things. Go and take me some drugs from a drawer, or do some cleaning. But when it's getting serious, right, if you would like to administrate some injection, then you can dive into that avatar, and, you know, then you can move the arms, and then the robot is moving, and you can see through the eyes of the robot in stereo. And then you can take an injection device and go to the human. Well, this is a PhD student, and this is not a real injection device, but, you know, it's a proof of concept, and you can give an injection within minutes, right? So that's the vision. But then you would like to have a human to control that. You don't want to have the AI-based robot doing that. But altogether, you can do, you know, a kind of a ecosystem to address this. People who need it even more are people with serious disabilities, right? And here you would like just to enhance the capability of the human. These are, again, our PhD students, but you have a robot arm with a wheelchair and with a muscle and neural interface, and then the robot arm helps these people like Stephen Hawking, right? They cannot move anymore, almost not at all. But with the aid of the robot, they can, you know, live almost, well, they can do some things independently. And I'm coming to the end. One highlight for me was the participation to the Cybathlon. This is a competition organized by ETH Zurich. Could you please click on this video? And this is organized every 4 years. It's kind of an Olympic game of people with disabilities. Excuse me, could you try to click on this video because it's not starting somehow? No, going back. Just on this image. Oh, okay, thank you. So this is Matthias Atzenhofer. He has a very serious muscle disability, so he cannot stand up, he cannot move the arm, he can control a joystick. And the competition at ETH Zurich was 10 minutes, 10 different tasks from the household. And we were the only one to solve all the 10. The second place was a French team. They solved 9 of the tasks, and ETH also solved 9. But it's just because, you know, you have the interaction of perception, control, and the human manipulation. Because, you know, when he grasps the object, he has a camera, the object is detected, and basically the control and the AI helps approaching the object, right? So he succeeded to grasp objects from the floor, you know, manipulate also some clothes and so on. And I think these people, you know, even with the limitations of current robotics, these people can have some benefit of robotics today. And again, you still can have the teleoperations or the call center to help them if they need help. So, you know, it was about grasping some clothes and putting them on the armchair, and then opening a door and passing through the door and so on. So more or less, that's the state. And this concept of, you know, having robots helping in homes, in hospitals, but then having the call center where people can, you know, log in and help if the AI is not working. No? Yeah, I try to show you the whole screen. And then maybe that's a better way than just shooting directly for the whole humanoids market, right? But starting instead with, you know, these people, it's a small market, but people with big needs, and then you start collecting data, because those people generate data while they operate a robot, and using this data, you can start training your neural networks, and then maybe come one day to the big market. Maybe that's a, you know, an easier approach, and these people are starting now a company, hopefully end of the year, than just shooting to the end of, you know, to the top of the line with millions of robots for our homes. I don't know, the future will show it. So we start with direct control, and then shared control, supervised autonomy, and then full autonomy. And yeah, maybe starting with early adopters, addressing market needs, and then going towards the mass market and towards the stream of robots everywhere. On the way, we generate a lot of startups. So we have in Europe an ecosystem of companies, not only the big ones like, you know, well, Kastanienbaum was also something Sven was involved, but now Agile Robots and Franca Emica, but also companies doing sensors, motors, you know, components, vision, and so on. So I think we have an ecosystem which helps getting a whole robotics industry, so I'm positive about that. And I will end by, you know, around 2002, could you click again on the video, please? Around 2002, the robot soccer community said by 2050 they would like to play football and win against the world champion. So now we made this video last year when we had the World Championship in Europe. It's okay, it can shoot some goals far away from humans, but it's half-time, right? It's half-time, so, you know, who can say if in 50 years they will win or not? I'm not sure, but now, to answer the question I was asking at the beginning, yes, for sure it's a hype, right? Humans won't come in 2 to 3 years to the market, we all know, right? But I think the trend is here to stay because there's so much money in the system. So in the time frame of 10, 15 years, I think they will transform our lives in an unprecedented manner. I'm pretty convinced of it, and I hope, you know, I'm trying to ring the bell. This is a video generated by a picture generated by ChatGPT by Wolfram Burger, to ring the bell and say, people, it's serious. We need to do something in Europe. We need to be part of it. We should not leave it just to US and China, but we need an industry, a strong industry on robotics in Europe. We have the scientists, we have the knowledge, but we need to scale up. And I'm worried that we might miss the scaling in Europe, because we move too slowly. So altogether, I think we need to push for that, and then I think we have a good future for robotics in Europe as well. Thank you very much for your attention.
Thank you for your inspirative talk. We can still afford several questions from the audience, and then we can continue during the coffee breaks. Giuseppe.
Thank you, Alin, for your great and inspiring talk. It was really impressive. Since I have so many questions, I will make the journalist questions. Where do you see the market to be in 5 years? And what is, in your opinion, the role of China in this humanoid market?
Yeah. So you are completely right. It's, you can see the market for billions, but nobody can see the market for 1,000 humanoid or 100 humanoid robots, because that's really difficult, right? And I was trying to show that with this exponential curve. So maybe starting by addressing people which have very big needs, right? They are happy if they can drink alone a glass of water. If they take it 5 minutes, they are fine, but they do it alone, right? So no, maybe starting with those applications, either where it's very expensive, like space, or where people have very big needs, right? Of course, there's all this security and military. I don't want to build Terminators, right? So I don't want to talk about that. I'm worried a little bit, honestly, but let's start with space and healthcare and so on. And a Chinese, I mean, it's impressive what they do. They are so fast in developing hardware, right? And I just bought a humanoid, 90,000 euro, right? And it had a lot of errors, and they were upgrading continuously. So I think their ambition is to dominate the hardware market. I don't know about the AI. Maybe the hardware will come from China, the AI from US, I don't know. And then what are we doing in Europe? We need an answer, yeah.
Hello. You mentioned that you want to build an ecosystem for joining the forces and also to provide some solutions for everybody. How want to achieve the interaction between the partners in this network, and how to bring them to to give solution to the community?
Yes. So first of all, I'm sorry that I did not put a QR tag. But if you Google for AI on demand or for Eurocore, so European core, right? You will find this platform where we organized, this uploading of data and code. So, and I do not like to impose things top down, right? So I don't want to say there should be exactly this software and this platform, but rather, stimulate the ecosystem to cooperate. So we have this competition where you get points if you cooperate. We have this infrastructure where I really encourage you to go and browse through this. Because I know labs who, they said, I'm doing only tele manipulation. I don't have perception, I don't have planning. Then they went to this cloud infrastructure and they could download some elements. So just go for Eurocore and AI on demand, and we are trying to build something there for Europe. And what I did not say, our network has a deadline in 1 year from now in the European Parliament, where we will go with all the robots and do live demonstration to the parliamentarians and to the commissioner. And I hope very much that we can convince them to put some serious money into robotics. So much more than we have today, to tell them, look what's going on in the US, look what's going on in China. We have excellent researchers and scientists, but we cannot create a market. All you around here and myself, we cannot create a market. We need the industry and we need politics for that. And I hope to ring that bell, right, and to convince the European Commission to do some bigger initiative. I don't know, let's see.
So I will exploit my role of the moderator to ask my question, because we discussed already about the market, and I think it's also very relevant to discuss a little bit about education. You mentioned several times this, let's say, clash between control theory or model-based control and learning, or call it maybe even better symbiosis, not the clash maybe. Now we have a lot of students interested solely in learning. So, but I think that we all agree that to solve complex tasks, we need to use really symbiosis of model-based control and the learning. So how you approach your students by explaining how the control theory, how dynamics is important to solve these questions, so not to look only for learning. So what do you say to your students?
Yeah, I mean, you are mentioning a very important point, right? And I mean, that's also our role as professors, right, to educate the next generation. And there's a danger, right, because they get these videos of YouTube robots doing something with reinforcement learning that at the end they become just data curators, right? They just telemanipulate, you acquire data, you drop everything in a big neural network. And I'm pretty convinced that if the next generation does not get the basics, right, we will run into a very serious problem. I know what you're talking about. In my lecture also students said, okay, I can understand the mathematics, but why are you teaching me all these things? He just asked that, right? And I said, I'm pretty sure, right, that if you will have a generation which only relies on curating data and not having the basics, we will get into serious limitations. So I'm absolutely convinced that you need the foundations of robotics together with data. Yeah. And it's our role actually as professors to continue teaching them and tell that to the students.
Okay, so Okay, we have 2 more questions, that's it, so be fast.
Yeah, so thanks for your presentation, Alin. And actually, I have one question about the structure of the humanoid robot. Because actually, I have seen in China, we have a lot of the human robot company. They have structure, like have the legs, have the shadow hand. But actually, for the commercialization, they do not have a lot of application scenarios. Actually, when I go back to China, I see a lot of mobile robots with a platform with wheels. They are commonly used in the hotel, in the restaurant. So how do you think about the basic structure for the humanoid robot in the future?
So we discussed that before again. Today, you don't have a clear market where you need purely a humanoid. So you can solve every individual task by a more specialized robot, right? And maybe for service robotics, as I mentioned, hands are more important than legs. So maybe you need 2 arms and a dexterous hand, maybe not humanoid hand, but a dexterous hand, and mobility and 3D stereo to solve problems, you know. I mean, we all agree you need stereo vision, right, and a mobile head. You need a mobile platform, and you need more than 1 arm, right? Whenever you try to assemble your IKEA furniture, right, with 1 hand, no way. You need like 2 or 3 or 4, right? So I think these are the key elements. If you need legs or not, okay, it's debatable. But you know, the argument of those people is, if you do specialized robots, you will never scale up to the number that the mechanisms of production, like for the iPhone, work. Right? You need to fabricate millions of that. And if somebody tomorrow tells you you can sell 10 million humanoids, redesign your entire production process for 10 million, then your humanoid, you know, the prices will drop dramatically. Probably they will cost less than a car, less than 20,000 euro, 10,000 euro at the end, right? But the question is, when is this iPhone moment, right? The point where the phone is not something for you know, some special customers, but for everyone. I don't know.
Thank you. So, very last question before coffee break.
The coffee smells out, so I wish just one visionary question, because your presentation, Alin, triggered me to discuss a little bit about perspectives of humanoids. Many people here in this hall belongs to as successors of Vukobratović School, model-based, as myself from Mikhail Pupin Institute. But in this moment, looking your presentation, maybe I can conclude that AI nowadays run a little bit in advance in comparison with mechatronics. That means that AI and application on humanoids and generally on robotics, the progress of development is faster than mechatronics. If we compare period from Honda Asimo in 2000 until nowadays, we see that the robots in technology sense, nothing radical, nothing epochal happens. We have motors in the joints, we have shell, rigid body. My question is, 2 main problems for humanoids in the future are power, autonomy, and physical manipulability. Mm-hmm. Once our friend Dr. Uwe Haas told, I remember it, human eat 1 banana in the morning and can operate all the day.
Me not, I need more.
Yeah, but it is a great problem for humanoids, it's the mass. Yeah. So I think that the progress of working in building artificial muscles, so going towards polyarticular actuation and new materials like electroactive polymers, artificial skin to enable smart sensing and so on. I think that it gives the new push to the humanoids. In this moment, I cannot believe that at such stage of development we will achieve a high performance of humanoids. What is your opinion as an expert?
My answer has two parts. First of all, I would say that the mechatronics, you are right, it's far away from human performance, but when I compared mechatronics and AI like 5 years ago, mechatronics was good enough, let's say, AI was bad. Right? You are not able to localize objects, manipulate objects. Now we have a big jump in AI, right? So AI is catching up and going to the physical world, and everyone is excited. And I would say the mechatronics we have today has a lot of limitations, but is good enough for the first applications. That's my first answer, right? We need a progress in AI. My second answer is, yes, I'm researching myself a lot also on compliance of robots, about how to use resonance, compliance, and so on. So we need also next wave of mechatronics, right? And I did not present because just I decided to focus on this, but I had an ERC advanced grant just on compliance for robotics, right? So this is a topic very close to my heart. But maybe we have 20 years of torque-controlled robots, mature robots. Now, if the AI comes on top, you can start developing. And in parallel, we will develop the next wave of more biologically inspired anthropomorphic mechatronics. Maybe that's a way to go. But I fully agree with you. Thank you.
Thank you. So I think that Alin answered a lot of questions to deserve the certificate from the organizers.
Thank you. Thanks a lot, Costa. Thank you. Thanks a lot. Yeah. Thank you.
So not to allow coffee breaks are distracted by the technical session. I recommend we have like half an hour coffee break now and start with the sessions at 10:45. See you on the fourth floor.